Hi all. Today, we are going to see the topic of matrix decomposition and its applications. I'm Sriranjani Ramakrishnan, Google developer expert in machine learning. Thank you, Usha, for coordinating this meetup, and let us go to the topic directly. So before actually going to what is matrix decomposition, let us have a motivation problem, and then we can see how matrix decomposition can be used for the problem, right? So the most common problem when we say about matrix decomposition is the recommendation system because it's more popular. So consider movie recommendation system. And in movie recommendation system, I'm going to have movie being rated by every user, and you have a history of ratings of which is obtained for different movies from multiple users, and the rating scale is from 1 to 5, right? If I want to represent this as a matrix, then what I do, I just have to represent the matrices R, and where every row is going to represent the user who has rated a movie from 1 to 5, right? And this also means that every column is for a rating of the movie, right? Now, consider this as a matrix. Now, the main issue with this matrix is that it is sparse. Why? Because I might not rate all the movies which I watched, and similarly for different users. So this matrix is not fully filled, and fully filled is also called as a dense matrix, and this is going to be sparse because only very few entries are being actually filled, and all other question mark, which means it is a missing entry. Okay, so the problem in hand is that what if I want to actually get a compact representation of a user preference for every user preference with this particular input matrix? And the second question is, how are we actually going to predict the rating of the missing entries? So these are the major two problems which we are going to focus on today. And the issue is that the matrix is sparse, and also consider the scale of the matrix. Say, for example, if a matrix is going to be like really huge with, like, say, a million rows and a column, then how can we apply methods to solve the issues? So computational complexity for a large scale matrix becomes a big issue. So what we're going to see today is that using matrix decomposition, how can we solve this? And of course, this is one way to solve the problem. The other thing which I want to say that in today's talk, we are not going to actually define mathematically the exact correct definitions of every topic or the concepts we're going to see today. The main aim of today's talk is just to take the major message from the topic and not mathematically correct about it. So because you have a lot of good tutorials as well as lecture talks where they have actually defining mathematics correctly about it. And let us go to the topic directly. So now we got motivated, and we are going to carry forward this whole scenario till the end. And let us see why matrix decomposition is very important. Okay, now we just give a puzzle. Is it possible for you to find the next number in the sequence if I give you this set of numbers? You can just think about it for a while. Say 36, 216, 1296, 777, yes, it all ends in 6, that's one thing. But otherwise, it is very difficult for us to find the next number in sequence without knowing the actual structure in the system, right? So what we are actually saying is that if I can decompose the number into smaller components, say for example, into its prime factors of 2 and 3 and its powers, then it becomes very easy for me to predict the next number in the sequence. So the next number is going to be 2 power 6 into 3 power 6, right? So that is the major, concept behind matrix decomposition also. Like how we are taking a number which can be decomposed into its prime factors to know the structure of the numbers. Matrix can be viewed as a complex representation or arrangement of the numbers into rows and columns. So matrix can also be decomposed into product of smaller matrices, and so that we can understand the structure behind it, and that can be used for further understanding of the data. So that is the major idea behind the matrix decomposition. Now, what if I say for this rating matrix which we saw earlier, it also has a structure, right? Say for example, column 1 of the matrix can be written as column 2 plus column 3, or column 2 can be written as 4 times column 4. Then it becomes very easy for us to fill the missing entries. So that is what we will be trying to do, which means that if we are able to find out the underlying structure in the matrix, then we can fill the entries, right? And also by means of it, we will also be able to find a compact representation of the data. So before actually solving the problem, let us understand some basics. So a rank of a matrix is defined as the number of linearly independent columns. So what does it mean by it is that every data we are usually representing it as a column vector, right? So we are going to see that we can say that a rank it could be the number of independent features which we have for the data. So how many number of such independent feature vectors we have, we are going to call that number as rank of a matrix, as simple as that. Say for example, in the numbers you have 2 and 3. So consider that it could be like 2 numbers, which could be like a linear, but that is not the correct way to represent it, but just intuitively that's how we say. So rank 1 matrix means there's only one linearly independent column, and rank 2 matrix means you have 2 linearly independent columns to represent the whole data space. So we can thus say that rank K matrix, right? It can be factored into a product of a long skinny matrix with K factors, and also a short and a long matrix, which is going to have the K rows, right? So this is what we are going to call it as a matrix decomposition, where you are having a matrix A, which is going to have n linearly independent column, which means I'm going to have n rank for this matrix, but I want to represent the rank n as, or decompose it as, 2 matrices, which is going to have one is rank K and then rank K times n, right? So what this is going to give us, it is going to give us a compact representation in terms of K, and how it is useful we can see later. But this is the major idea behind the matrix decomposition. This is also called as a low rank approximation, because the full rank of n is actually reduced into a lower rank of K. So this is the major concept which we can use it for multiple other applications. So I hope this concept is clear. So now let us keep this thought process and next we are going to see about Eigen Decomposition. So let us come back to the recommendation problem later, but before that we will just see about some topics, and then later we can go about how we are solving these recommendation system problems using the concept which we learned. So the first we have learned is this rank and how you can use a reduced rank representation for it. The second is going to be eigen values and eigen vectors and eigen decomposition. So why eigen values are very important? I think people who already know about it. It is the non-zero set of vectors, which when applied on a transformation matrix A is going to retain its own direction, but it is just going to get scaled by a factor lambda, right? So this is what we will say, that if I am going to apply a transformation matrix A on a vector, and then it is going to retain its own direction, and but it just gets scaled by the factor lambda, then this vector is called as vector, and then the lambda scalar is called as eigenvalue, right? Which shows how much it is gets scaled, right? So now here you can take that this is going to be my vector, and if I'm going to apply a transformation, just use lambda times, it just goes on top, and it gets scaled on x and y axis, but it still retains the same direction. If you're going to take this, you're going to see that image is represented as pixels. Then if I want to apply a transformation, say here, you can see that this blue vector, which is an eigenvector, is still retaining the same direction, right? But the red vector is actually moved its direction. So this blue vector is called as eigenvector, but this is a normal other vector. So that's the most important property of eigenvector, and how it is going to be useful for us. Say, consider that you have a matrix here, and if I want to represent or decompose this any given square matrix, which is having n linearly independent eigenvectors, then we can say that if you're going to stack all the eigenvectors of a matrix as a matrix, then you can decompose this into eigenvector matrix, eigenvalue matrix representing all the eigenvalues along the diagonal as a diagonal matrix, and the inverse of the eigenvector. So that this is called the eigen decomposition. So that's been represented here, where A in matrix, which is a inverse matrix, can be decomposed as D, which is having as columns, and lambda, which is going to be a diagonal matrix with eigenvalues, and B inverse, right? So the inverse of the eigenvalue. So this is the most important takeaway of this slide, that you can decompose any matrix, a square matrix, into this. It also has a property which I'm not going to go into detail, but then if the matrix is going to be symmetric, then it has a nice property that B lambda, and then it's going to be B transpose. So B might not be the correct word, maybe it is U, but which represent that if the matrices, if the values are going to be orthogonal, if the columns are going to be orthogonal, then it means that it has a nice property of decomposing to U lambda as well as U transpose. Okay? But the major takeaway of this eigen decomposition is this, that you can decompose into this. Now, let us see. So first we saw how we are defining the rank, and then how using rank we can decompose a matrix into a product of simpler matrices. The second, we saw what is eigenvector and then eigen decomposition. The third, we are going to see about PCA. So principal component analysis is one of the most commonly used method for converting correlated high dimensional data to a decorrelated low dimensional data. So majorly it is used for feature extraction, and then low dimensional representation, dimensional reduction, etc. But this eigen decomposition is a major part of the concept behind the principal component analysis. So what we are going to see here is that PC in a nutshell. The slide looks very crowded, but I can just explain here that first, suppose you have a correlated higher dimensional data, then what are the steps, to go to the PCS, what we're going to see here, and how Eigen decomposition is going to be useful to this, calculation of the PCS. So the first step is that you're going to center all the points, and you actually want to find the dimension which is of highest variance. So why it is important? Because if I say that if I have all n linearly independent feature dimensions, I want to take the ones which is going to provide the maximum amount of variance in the data. So in order to find that, the best way is that you're going to take every column and try to find the covariance between the two columns, right? So finding the covariance is going to provide me a matrix which is going to contain the covariance between every columns in the data matrix. So that is what you're going to do. And so say suppose H is going to be a column, mu is going to be a column, and then you're going to say that you're going to find the covariance. Now, after finding that, I am going to calculate the eigen vectors as well as eigen values of this particular matrix. So that's what we are doing here. We will be calculating this covariance matrix and its eigen values as well as the eigen vectors for it. Okay, so you're going to use the eigen covariance of data. After calculating the eigen decomposition, you can actually arrange or in sorted order of the eigen values with in a descending order with the highest eigen values and its corresponding eigen vector in the matrix, and then pick only those eigen values which is of having higher strength, right? We don't want to go towards the low strength eigen values. So that is what is the main concept here. Basically, you are taking the eigen vectors, the eigen values, which is going to have the highest strength. Once you get the eigen values as well as eigen vectors, you are going to project all your data points onto the dimension which is having those eigen vectors arranged in the order of importance. And once I get the new data points, you're going to, basically you are getting a uncorrelated low dimensional data, right? So what is the takeaway from this? It is that principal component analysis, generally you are using it for feature dimension as well as for feature dimension reduction as well as for feature importance, or feature extraction. So how we are doing it? Mainly because we are calculating the covariance matrix and actually doing the eigen decomposition. So basically that is what we are finding the eigen vector and eigen values, which we done in the previous slides, right? So that is how we are doing a PCA. Now, let us talk more about a PCA with an example, and we will see how we can relate it to the recommendation system, a problem which we saw. Let us go to this principal component analysis for eigen basis problem. So, for example, you are going to take data from which is going to contain 400 images of faces from 40 people. Right? So the problem in hand is that you want to find out the principal components of this data set and how you can represent it, compact representation, right? So each of the data, like image, is going to be 64 cross 64, which is like 4096 dimension, and you're going to basically stretch out and write every face as 2096. So totally your data matrix is going to be 400 plus 2096. Now, what we want to know, like we want to represent this using a low dimension representation, still be able to capture all the important factors, right? So principal component analysis, which we saw earlier, is going to be useful for this, right? What we are going to do is we are going to take the eigenvectors of the covariance matrix of this particular data, which is going to be obtained using X transpose X. And I assume your X transpose X, you know that it's a product of the transpose and will be a matrix itself. And once you get the covariance matrix, as we saw earlier, we are going to find the eigenvectors of the covariance. So that is going to give me the most important feature components of the data, and here those are called as the principal components. And here we represent the principal components creepy, guys, because it's really creepy, but they are the most important representation of the data. So here for this 400 rows, you're going to get 400 principal components because the branch is 400. And the most important factor here is that when you sum all these 400 components in a linear combination, you can get back each of the traces, right? So that's the most important thing. So each phase actually is represented as a linear combination of some scalar of each of these, creepy guy, which is the principal components, right? Phase 2 is another linear combination, right? So this gives us a nice structure of decomposition of each, high dimensional vector into linear combination of these vectors. And this principal component is actually going to represent one specific aspect of the data. Say, for example, it could be like one typical representation of a person with glasses. It could be a typical representation of a person with a smiling face, or a person with a big nose, or a person with a old age, something like that, right? So each of the aspects is going to get captured by these principal components, and these aspects are called as factors, basically, which helps us understand, okay, how many such latent factors are there, like what actually the data is containing, right? So it's actually helping us to understand more about the data. They are the specific complex representations. So now we saw that you can apply a principal component analysis, which uses the eigen vectors to get the most important feature factors as well as reduce the. Now let us go back to this recomposition problem we already have, that I have this R user rating matrix and for a recommendation system. And consider, for example, that if I have the matrix like really filled, like all the entries are filled, and if I want to calculate the user principal components or the movie principal component, then how do I use the PCA to do it, right? So you're going to basically do the PCA approach on the fully filled user rating matrix R, and then each row is going to give me all the users components, and R transpose is basically going to give me all the movies representation components. So Alice can be represented as some linear combination of the aspect, which is, say, action fan, comedy fan, etc. So this concept is giving us a semantic meaning, like whether Alice is more of a romantic fan than action or a movie fan, right? The same thing can be done for a movie also, saying that Titanic is going to be more towards romance and less towards action, kind of thing, right? Now, let us hold this thought and let us try to see what all we saw. That we saw what is a rank, then we saw what is the eigenvalues and eigenvectors, and how we can decompose a matrix into eigenvalues, eigenvectors. Then we saw how principal component analysis is useful if I want to convert it to a high dimensional correlated data to correlated data to a low dimensional decorrelated data. And we also saw that if I am going to use this PC on a user rating matrix, how I can get the principal component or the aspects of the latent factors for it, right? The issue with the PCA is that, first of all, it can be applied to a symmetric matrix, and sorry, not symmetric matrix, sorry, a square cross one, and it can be, it is very sensitive to scale variations. It also cannot be applied to any rectangular matrix, which is a cross one. It needs orthogonality constraints, so it cannot be applied to a case for non-orthogonal data. And also, if there is any non-linear structure in the data, then principal component analysis cannot be generally applied to such cases. So all these are some of the drawbacks of principal component analysis. Of course, there are approaches to solve that using probabilistic approach, kernel PCA, etc. But we are not going to go into this. The main concept is that what if I want to apply such concept to a rectangular matrix which is more stable and which can give me a better solution with reduced complexity. The other issue is that calculating the covariance matrix, of a data which is like a large scale matrix, and calculate like an X transpose X for a large scale matrix and its eigen vectors is really computationally costly. And in order to avoid this, we want another approach where solve this problem, and that approach is called as a singular value decomposition. So singular value decomposition, what it does is that it is just directly going to take the data matrix X and it's going to divide into three factors, which is U matrix, S matrix, and then V transpose. I'm going to explain what is all these things, but the major takeaway of this is that single value decomposition can be applied directly on the data matrix and not on the covariance matrix, and that solves us a lot of that reduces a lot of computational costs for us. And whatever PCA gives us, right, the eigenvectors and what are the eigenvalues and what are the importance and the latent factors can directly be obtained using a single three-factor decomposition, which is U, S, and V transpose, right? So here U is going to be orthonormal. So what is orthonormal is basically you're going to have orthogonal and with a normal constraint, and all the factors are represented here as a n cross n matrix, and then D is going to be the diagonal matrix containing the singular values, and V transpose is going to be a D cross V matrix. So these are the constraints. So V transpose V is I and V transpose is I. We're not going to go into that, but this is the main concept of the takeaway from the singular value decomposition. And how it is related to PCA. So it is related to PCA because applying singular value decomposition on X, like applying a PCA on X transpose directly. X transpose X is the covariance matrix, right? So that is what it is, and yeah, that is what it is. So let us now go to applying how singular value decomposition can be applied to the recombination problem and how we are able to solve the problem, right? Okay. So suppose as we saw earlier, so there is a notation confusion here. So R is going to be the rating matrix, and how when you apply SVD, you're going to have U, S, and V transpose. Here we are going to represent that as M, sigma, and U transpose, right? M, sigma, U transpose. All the rating matrices are. So this is the apply SVD. So what it is going to give us? So M, the columns of M is, will be able to build back. The columns of M will build back the columns of R from the rating matrix, and the columns of U is actually going to build back the rows of R. And both the M as well as U are going to be orthogonal, which means like the dot product value is going to 0, and the sigma is going to be diagonal, right? So now you can see how we geometrically can represent the SVD here. Say suppose I have the you have the vectors, and if I want to apply a transformation K towards this, then using SVD, you can see how you can decompose it into this, which means that when you are going to apply the transpose, it's going to just get rotated here, and when you do a sigma, it's just going to get the scaling version of it with all the single values, and then you're going to just rotate it back towards the same direction, right? So this is equal. These three steps are like equivalent to transforming this directly to using the transformation matrix. So by doing this approach, you are still able to get the in-between components and how it is actually happening, right? So that is what is about the SVD. Now, suppose I'm going to apply SVD on this recommendation system. You're going to see that RUI could be each of the values of the rating matrix U and I, rows and columns, and then you're going to it can be like given as a dot product between the two vectors, which is PU vector, which is specific to a user, and also a column vector, which is for the item, which means that for the movies, right? So this is going to be a column of U transpose, and this is going to be the row of M, right? So that is what, and this. So basically, you can write RUI as dot product of PU dot QI, right? So that is the major takeaway of this particular thing. Now, which means that I can represent each user as some linear combination of the data factor, right? And similarly, a movie as linear combination of latent factors. So you are basically getting all the strength of the values or the affinity of how much it is using these PU, which means the user vector, as well as it's going to be the movie or the item, right? So when I say that RUI is PU.QI, it can be seen as the affinity of the U for the latent vector for F, and into affinity of I, which is the movie for F, right? So you can just take F from all the multiple latent factors like action, comedy, romance, etc. So that's how you're going to represent it as, and this is possible because of the SVD. So initially we saw that we have two issues, and one is going to be getting a compact representation of the latent factors, and second is filling the missing values of the matrix itself. What we are trying to say from here is, because we are able to get this decomposition, if my matrix R was dense, right, and if you're going to apply SVD on it, then we could calculate the M and U matrices as eigenvectors of R transpose and columns of U as eigenvectors of rho transpose, and the eigenvalues are going to be mentioned in the sigma. So that's how both are variable, like U. So there are two concepts which you have to see. One is this matrix A can be decomposed using SVD into U, S, and V transpose. So here the U, S, and V transpose is written as M, sigma, and V transpose, which is U transpose here. The second thing what we are seeing is that how are we actually getting this U matrix, right? So the U matrix or the M matrix here is just obtained by eigenvectors of R transpose. So the leading matrix and its transpose is actually going to give me that of eigenvectors of R transpose is going to give me the columns of this, and eigenvectors of R transpose R is going to give me the columns of this. And the eigenvalues, whichever is associated with this, is being mentioned here with this matrix, right? So this whole thing is possible if all my R values or the leading matrix is going to be filled, right? But we have another issue is that R is sparse, right? So first thing what we have to do is that we have to fill the missing values. So first problem we saw was that we have to fill the missing values. Suppose I can fill the missing values using some simple heuristics like mean of the rows or columns. Then you can perform SVD and you can get into latent factors. So that solves both our problems that you're already filling missing values as well as getting the compact representation of the latent factors to the user data. But you can also go for a more sophisticated solution if you feel that filling missing values as a mean of column, which is like very simple. Then in that case, you can ignore the missing values of the R, right? And you can directly solve the problem using an optimization problem, which is inspired using SVD, inspired by SVD. Basically, you assume that whether the rating is filled, and then if it's going to be given as a dot product of P and U, then how can you just solve it as an optimization problem to get the best value for P and U, and then use it to get the values of P and U and get the values of P and U. And that is this optimization problem is going to be solved using stochastic or any other. So basically, we have skipped the details here because it involves much more math and understanding. But that is the basic concept. So by doing that, I am able to fill the missing entries, and once I fill the missing entries, I can perform SVD on it to get the latent factors. So that's how we are able to solve this problem of recommendation system. This is like one way of solving the problem of recommendation system using matrix decomposition. The other most important point about this singular value decomposition is also that you can have reduced low rank approximations, similar to how we saw for the initial few slides back. We can reduce the number of latent factors into some K factors. So if I have a L cross V matrix, then I can say that if I want to take only the K vectors, then I am just going to take the first few K vectors and then its singular values, and then it's row alone. By doing this low rank approximation, we are able to get similar results, and that helps us in improving the computational complexity of the problem also with respect to storage as well as time. Right? So that is the major advantage of using SVD approach. So this SVD approach, now we saw that how SVD is useful and how it has been applied to a recommendation system problem, and how using SVD we solve the recommendation system problem of having missing entries as well as finding the latent factors, and also how it can be helpful for a low rank approximation itself, right? So we now saw the example of recognition system, but the approach is quite robust, right? It can be applied for any such data matrix and any domain, right? So now we will be seeing the application of this SVD for image compression problem as well as a topic modeling problem in natural language processing. So we can see that the same concept, you're going to represent the image as pixel and it is going to actually have a rank of 200. But we already saw that with reduced representation itself, we can get back the original image, right? So that is the best takeaway. And you can see now with 50 rank itself instead of 200, we are able to get back the image itself, and that is because of the SVD. So you're going to take the story space of m plus n instead of m into n. You're going to take m into n, right? So that is the beauty of SVD. Yeah, I mean the most important thing is why and how we can do it, because we are already keeping the eigen values in a sorted order, and we are just taking only the eigen values which is of higher strength and its corresponding vectors, right? So that is how we are able to do this eigen. It is a single value, whichever the matrix. Now, consider for topic modeling. So topic modeling is a very important concept in the natural language processing application. So here you're going to take a document, and a document is represented as a number of different words. And you can represent the documents as rows and the word as a column values, like the words which is appearing in the document. Suppose in this document term matrix, yes, I want to decompose to find the topics, right? Which corresponds to the latent factors, similar to the concept which we learned earlier. Then you can again use SVD to factor into three things. So like the first U matrix, which is going to be the eigen vector of we saw, right? X transpose, and then X transpose X, and then S is going to be the singular value matrix, which is going to have the ones which is the singular values, and then you're going to take right eigenvector matrix, which is going to be which is going to have the remaining concept of XX transpose. Now we can see that the rows of this matrix is going to have the topics, and the values in each row is going to say what are the importance of words in that particular topic. Right? So that's how we are able to model topic modeling using this. There are much other methods for all these applications, but using SVD, how you can solve the problem. So that's what we saw. So as summary, we saw that how matrix decomposition is actually useful in decomposing a matrix into smaller matrices, and we learned about Eigen decomposition, and we saw what is principal component analysis and how it can be applied to one of the exemplified cases, and how Eigen decomposition is used. And then we saw the disadvantages of principal component analysis and how singular value decomposition comes into the picture. And we also saw how singular value decomposition helps us in solving the problem of recommendation system, and it can also be used for image compression and topic modeling applications today. Yeah. So I think you all can use a singular value decomposition as well as principal component analysis now, and we'll see that how you can apply for multiple applications. Right? Yeah. So these are my references for the talk, and here I have intentionally reduced the math because to cater for general audience, but people who are interested in more mathematical concept, you can definitely go through Stan's lectures, deeper Stan's lectures on these concepts of values, vectors, decompositions, value decompositions, etc. And there are very good resources on the other concepts of linear algebra also, and how recommendation systems and there. Thank you so much for listening to my talk today, and also thank you, Usha, for coordinating this event. You can follow me on LinkedIn